Hello Naseem, am I audible?
Yes, you are audible. The screen is also visible.
Okay. Okay, so we'll start today's class. Good evening, everyone. I am Somodeep from Indian Institute of Science, and I'm taking this TA sessions for the course Numerical Methods for Engineers, which is being presently taught by Professor Niket Kaisare on the NPTEL platform. So this is the 10th live session, and here today we'll be talking about ordinary differential equations. Okay. So till now, last two classes, we had discussed about numerical differentiation, numerical integration, all those topics. And today we will be seeing how we can utilize the concepts of numerical integration and numerical differentiation to in solving our ordinary differential equations using different numerical techniques. So first we'll look into uh, what is called the first class of problems is known as the initial value problems, or IVPs. So what are initial value problems? So initial value problems are such kind of problems in which a differential equation will be given to you, and also so first we need to understand what is the motive of a differential equation. Suppose we have a differential equation as like this: dy by dx equal to x. So this is a differential equation, right? Why is it called a differential equation? Because the differential operator is applied on a particular variable y. So dy by dx is a differential operator which is being applied on y, and we have some other terms and an equal to sign. So that's why it is called a differential equation, not your normal algebraic equation. So here this differential operator is involved. That's why it is known as a differential equation. So just forget about numerical techniques. Just in class 12 or in our bachelor's, we have studied how to solve this normal differential equations analytically. So first we'll do that. Then we will go to numerical techniques. Okay. So this one we can solve by variable separation. So now if we integrate on both sides, it will be y, and that side will be y equal to x square by 2 plus c. So this is the integration constant, right? So what do you think is this y equal to x square by 2 plus c? If we plot this in the graph, how will it look like? So this c can take any real values, right? So it will be a multiple set of parabolas, right? So it can be y equal to x square by 2. It can be y equal to x square by 2 plus 1. It can be y equal to x square by 2 plus 2. Like this, infinite options are possible. So basically, this equation, if you look into y equal to x square by 2 plus c, this is a family of parabolas. So there is no unique solution of this differential equation. So it will be like this. One parabola can be like this. Another parabola can be like this. Another parabola like this. There can be infinite number of parabolas, right? It can be like this also. Because this C is not known to us, that's why we are not getting an uh, unique solution of this differential equation. So how can we get a unique solution? So in order to get a unique solution, we need to find out this value of C, right? So how can you find out C? So if some condition is given on your Y, some constraints are given, then only you can equate it and find C. Unless that is given, you cannot find the value of C here, right? So, so here comes your initial value. So it is, suppose in the question, initial value of the function is given to you. Suppose it is given y of 0 equals to 0. So it means that y at x equal to 0 is equal to 0. Means if you substitute y x equal to 0, your y is also 0. So this is given to you. So now if we substitute this here, y equal to x square by 2 plus c. So if you substitute this 0 here, x is also 0 plus c. So c you are getting as 0. So now if you again resubstitute back c, your solution is now y equal to x square by 2. So this is your unique solution, right? So once you have an initial value to your function, if it is given in the question, then you can have a unique solution to your uh, problem. Unless that is given to you, you cannot have a unique solution to your problem, and there will be multiple solutions to your differential equation. So is this thing clear to you? What is an initial value problem and why the initial value is important for us?
Yes, yes, it is clear.
Okay. Okay. So this was just an introduction to initial value problem from the analytical perspective. Now we will go into our topic. So what is our aim here? Basically, we will be given a set of differential equations and we have to solve those differential equations, right? Based on some initial values. And your dependent variable here for our analysis and all calculations here, we will take y as the dependent variable, right? There can be multiple different this variable, and x is your independent variable. So for our analysis, we have taken this as the convention that y is our dependent variable and x is our independent variable. So suppose we are given multiple differential equations in this form. This is one differential equation. This is another differential equation. Like this, say n number of differential equations are given to you. Okay. So if we write this in a compact form or the vector form, we can call it, it will be like this, right? dy by dt. Just we represent this differential by this dash symbol. And so this is your, in a compact form, it will be like this, right? So now if we, how can we solve this numerically? Analytically, we know there are many techniques, but how to solve this numerically? This is the main question here. So numerically, in any numerical technique, the main thing is your discretization, right? So one of the most important steps in any numerical solution of a problem is the discretization. So discretization is your main thing. So now you need to understand how we will discretize here. Right. So here your y is your dependent variable, and for the time being we are taking t as our independent variable, right? So in time domain we are trying to solve the equation. So suppose so this is your entire set. So suppose here there are some points. Suppose this is at Tn, the value of the function is Yn. Tn minus 1, value is Yn minus 1. Tn plus 1, value is Yn plus 1. So suppose here, in this type of problem, any one solution will be given to you, right? And the space between this discretized intervals is given by h. Okay. So suppose what will be known to you? The differential equation will be given to you. That is the relation between the derivative of y and t. Like it will be given first order I'm talking about, dy by dt will be equal to some f of t. This will be known to you, right? And initial value will be any particular value will be given to you. Value of say at point n it is known to you. Okay. Suppose this value is known to you. So value of yn at t equal to tn is known to you. So these things will be known to you. So now what you have to find out. So basically the unknown thing will be your value of any particular value. Say here, say we are interested in finding value of yn plus 2 at t equal to tn plus 2. So here your yn is given to you and you have to find out based on the relation which is given to you based on the differential equation. You have to find the value of yn plus 2. So now you can see here from to reach from yn to yn plus 2 based on the discretization what I have given here, you have to do two iterations or two steps. First from yn you have to jump to yn plus 1. Then from yn plus 1 you have to jump to yn plus 2. Right. Suppose if you were given yn plus 1 and you were asked to find out yn plus 2, then you would have only one step. So based on the discretization that you choose, that will decide the number of steps you have to compute, number of steps you have to perform in order to compute your the value of the function at that particular point. Okay. So now we'll just see here. Suppose this is our unknown, right? So now suppose the differential equation is like this, right? F of t. So now if we just integrate both sides, it will be like dy by dt integral f of t dt. This is from tn to say tn plus 2 we are doing, right? So here also it is from tn. Now if we substitute this, so dt will cancel and it will be basically yn plus 2 minus yn. But this f of this thing, f of tn plus 2, so this we do not know. So this is unknown to us. So unless this function is known to us, we cannot proceed in this way. Just by variable separation, what we were doing in the analytical approach, we cannot do like this. So this approach is not suitable. Okay. The variable separation approach, like our this thing, the analytical techniques, is not suitable here. So now we have to think it in some other way. What we can do? We can think of using the concepts which we have studied in the numerical differentiation. So what you can do, you can replace this dy by dt using our backward difference formula or the forward thing. Anything you can replace. So we'll try with backward difference here. Okay. Try to use just a second. So I'm not doing the derivation here. If you just replace this dy by dt as y n plus 1 n plus 2 minus yn, the backward difference formula if you replace, so basically you will get yn plus 1 will be equal to yn plus h into f of yn h square by 2 f dash of yn. So what is f of yn here? This is the derivative, right? So it is yn dash. So f dash of yn is yn double dash. So this is what we get if we replace this by our backward difference formula. But again, the problem is this we can use this using our backward difference approach. We can solve the equation and we can, but that will be more computationally expensive. So we have an alternate method to this also. So up to this, any doubts?
No, no doubts.
Okay. So what alternate thing we can use? So what we can do is we can expand our yn plus 1 or yn. Just suppose let us take a particular point x1 just for time being using Taylor series. So it is the same thing like the difference formula, but it is a different way of representing it. So we can, how we can write, say yx1 is x0 plus h, right? So now we can replace this by y of x0, h y dashed x0. So we can write like this, right? So from this, if we just manipulate some steps and if we do the derivation, we will get our iterative equation here. So this equation we will be using everywhere. This is known as the famous Euler's equation. Euler's. So this is the Euler's explicit method. Just remember this f of xi yi, f is here the slope function, right? It is the slope or the differential equation which is given to you. It is not the actual value of the function. Rather, it is the slope of the function at xi comma yi. Just remember this thing. So now we will try to understand it is fine, right? You are able to understand?
Yes, yes, it is fine.
Is it clear to you, Nasim?
Yes, yes, yeah, it is clear.
So this is my Euler's explicit method equation, right? So we'll try to understand how we can calculate it in a graphical approach. Just we'll try to understand how to do it using the graphical technique. Suppose this is t, this is y, and your function. This is the actual solution of the function, right? And we are given with the slope of that function. Suppose this is your Tn and say this is your Tn plus 1 and the gap between these discretized points is the step size h. So we'll try to see what is the slope here, right? This is the tangent to the curve at this particular point. So now, so this is the yn because it is the value of the function at yn plus 1. And we are interested in finding this value, yn plus 1, right? So this is the actual value of the function yn plus 1, which we are interested in finding. So what we are doing here basically, so I'll write it in terms of n only. Yn plus 1 is yn plus h into f of xi yi, right? So what is the f of xi yi? It is the slope of this particular line. So now if we just try to see what we are estimating here. So this is the slope, and what is the value of this? If we see in this triangle A, B, C, this is H, right? And we know the slope of this AC. So what we can write? Let us assume the slope is, what is the slope? It is f of xi comma yi, right? So we can write the slope as a, or rather BC by AB. So what is BC here? This entire length, this is h multiplied by f of xi yi. Just slope is given by f of xi yi, and slope is in this triangle. If we see ABC, it is BC by AB, right? So BC is equal to AB into the slope. So it is h into f of xi yi. So this much is h into f of xi yi. This much, and this is your yi, right? So let us assume this as P. So what is PC here? PC is yi plus hf of xi yi. So what is that? That is given by yn plus 1 or yi plus 1. So that is what we are estimating. This entire thing, if we see here, from here till here, so we should have estimated the yi plus 1 as PO, right? Because yn, the actual value of the function at Tn plus 1 is this length, PO, whereas we are estimating it as PC. So we are having some amount of error. What is that error? The error is given by OC, right? Just take some time and try to understand this one. Is it clear to you, or should I explain it once again?
Yeah, it is clear. I understood.
The
The
error
error
you
part.
understood how it is coming as OC, right? Because that is important.
Yes, I
Oh,
understood.
okay. So now why we'll try to understand why this error is coming. So if you see the figure carefully, you can see that if we reduce this value of h, that is, if our discretization is more finer, we have Tn here. Next, this Tn plus 1, the gap is huge, right? So if we just, this Tn plus 1, this is in our hands, what we are discretizing, right? So suppose we bring it here. Suppose this is Tn plus 1 dashed. So your h is reduced now, correct? So this is my h dash. So now if we see your new yn plus 1 dash is this value. And your estimated value is this length. This red line, right? Whereas your actual value is this one. This is your actual value, yn plus 1 dash. And your error you can see here, it has reduced. Just from the graph you can understand. The more closer you bring this Tn plus 1 to Tn, the less will be your error. That is, if h is reduced, the more finer discretization we can have on the curve, the lesser will be your error. Is this concept clear?
Yeah, it is clear.
Okay. So we'll see how with increase in age, how with reducing age, how is it reducing? How is the error reducing? What is the order of your increase and decrease? We'll see all those things. Just this is for graphical understanding how it is getting reduced. It's 2 minutes. I'll come back.
Okay, okay, sure.
Okay, so now this is about the Euler's method, and now we will see. First, we'll all see the theory, and then we'll solve some problems. Okay, through problems, we'll try to verify whatever we have discussed in the theory. So next is a new technique for differential solving differential equations. It is known as Runge-Kutta method or the RK method. So in the Euler's method, we were talking about how we can find the how we can estimate the value of y at a particular value of t based on the slope at y based on the slope at one particular point, which is at xi yi, right? So here what we will do, we'll divide the entire interval between tn and tn plus 1 into multiple sub intervals, and we'll find the slope at every sub interval, and then we will see how we can find the value how we can find the value of y at tn plus 1 in a better way or reduce the error. So based on the number of sub intervals, there are two classes of RK method. One is the second order RK method or RK2 method it is called. Another is the fourth order RK method, which is RK4. And RK4 method is more accurate compared to the RK2 method. Okay. So we will see here first RK2 method we will look into. this is t. This is y, this is t. And we have the function. So this is your actual function or the actual trajectory. And we have 2 points here. One is Tn here. Other is say Tn plus 1 here. So this is your h here. This is the value of yn. This is the actual value of yn plus 1. And now we will try to will take a random point in between Tn and Tn plus 1. So let it be the midpoint. Okay. So this is h by 2. So here I'm taking the midpoint. It can be any random point in between Tn and Tn plus 1. So it is h by 2 and h by 2, right? So now we will find the slope at all these points, right? So here, so this point we are interested in finding the slope, right? So first I'll look into what is Euler's method. Euler's method we will see and then we'll compare it, right? So the tangent, I'll draw it once again. So it is somewhat like this, right? So based on the Euler's method, this was my error, right? So this was the estimated value. This was the estimated value. Whereas the actual value was yn plus 1. So now here we will see what we are doing here. So what is known to us? Value of yn at t equals to tn is known to us, right? So what we can find out? So suppose it is given to you dy by dt equal to some f of t. So and y of 0 equal to 0. So this yn at t equal to tn is this one, y of 0 equal to 0. That is given to you. And you can find out from this differential equation, you can find out yn dash at tn, right? At t equal to 0, what is the derivative of the function? You can find out from this equation, from this differential equation. So now we can see we also need the slope of the function at the intermediate point, right? So how we can do that? So we have to find first y dash n plus 0.5 we are telling. Yn is at tn, yn plus 1 is at tn plus 1. At the midpoint we are telling it is n plus 0.5. That is a convention, okay? So now we have to find out y dash at n plus 0.5. So how we can do that? So this we can find out can be found using Euler's explicit method. What was my Euler's equation? yi plus 1 yi plus h f of xi yi. So now you have to be very careful here. So this equation gives you yi plus 1. That is at xi plus 1. This is the gap h. So here my gap is not h here. We are trying to find out yn plus 0.5, right? So yi plus 0.5, if I try to find out, it will be yi plus h into h, not h by 2 f of xi yi. So using this, you can find out yi plus 0.5. and this can be used. So now we have the two slopes, right? We now have two slopes. Yn is known to us at Tn, and Yn plus zero point 0.5 is also now known to us at Tn plus half. So we have two slopes. So now what we will do, we will take average of these two slopes and substitute it in the Euler's equation. So what we are basically doing here, I'll write the Euler's equation again. Yi plus 1 is yi. So here this was the slope, this f of xi yi. This was the slope at xi and yi. So basically in my Runge-Kutta method, in the second order technique, what we are doing, this everything is same. Only this f of xi yi, there is a slope at xi yi. We are not evaluating it at xi yi. Rather, we are taking the slope at 2 points. One at xi yi, other at xi plus half, yi plus half. Then we are averaging those two slopes, and then we are substituting it in your this slope function in the Euler's equation, and that gives me the RK2 method. Just a second. Just a second. Sorry, my iPad was not working. That's why. So you can see the screen now, right?
Yeah, it is visible.
Oh, it got stuck for me actually. Okay. So, so now we will see. So what I was telling is in Euler's equation, just understand the difference here. So this f of xi yi we were using, there is a slope at xi yi. However, here now in this RK2 method, what we will be doing is we will be using the slope at xi yi and xi plus half, yi plus half, and we'll average those two slopes. And that is a better approximation of this to estimate the yi plus 1. So we'll see why it is a better estimate, and we'll using the expressions we'll see. Using the problems, we'll see that. So now, so here we had taken a very this what is called the a particular point we had taken and in between, right? So this in between point, as I told, it can be anything. It can be at any point between Tn and Tn plus 1. So here we had taken a special case. So now we will see. Just a second. So just before this, we'll write the equations here. So iPad is creating a problem. So can you see what I'm writing on the screen? Is it working for you?
Yes, yes, it is working.
Okay, fine.
But
So this was actually the differential equation, right? So here in RK2 method, as I described, it will be so what we will be doing here, yi plus 1 is yi plus your h into f at xi plus f at xi plus half yi plus half. So this is my equation, right? This is the equation for your RK2 method. This RK2 method is also known as Hume's method. Just you remember these names, otherwise it may be asked in the question. Okay, so before going to RK4 method, we will see uh, two problems based on Euler's method and RK2 method. Then we'll go to the RK4 method. Okay. So just we'll look into the problems. So this is the differential equation which is given to you. It is dy by dt is equal to 2.5 minus 0.1 y square, and y at 0 is equal to 0. So we have to compute y of 2. So y of 0 is given to you and you have to find out y of 2 at t equals to 2. Right. So now the true value is given to you here. True value is y of 2 equals to 3 point. Just it is solved analytically this equation and the true value is given to you, right? So first we'll try to solve it using our Euler's equation. Okay. So this is the equation dy by dt 2.5 minus 0.1 y. So here we will first solve it. We'll solve it using different values of h and we'll see which one is more accurate. Okay. So first we will solve using Euler's explicit method. So first we will see h equal to 0.5. So now you have to see this carefully. So your value at 0 is given to you and you have to find out 2, right? The value of y at 2. So this is at x equal to 0 and this is at x equal to 2. Or rather here we'll do with t equal to 0 to t equal to 2. So now h we have taken as 0.5. So first we will our t equal to 0 is given. Next iteration next step we have to do at t equal to 0 plus 0.5. Next step we will do at t equal to 1, 0.5 plus 0.5. Next we will see at t equal to 1.5. Then we will go to t equal to 2. So the less value of h, if you take lower, so there will be more number of steps you have to perform to get to the actual solution. Is this thing clear to you?
yes, yes, yes.
Clear, right?
Yeah, yeah.
Okay. So now we'll start. So step 1. So Euler's equation is yi plus 1 is yi plus h into f of xi comma y. So first step, this is y of 0.5, right? This is y of 0, h is 0.5, f of xi is 0 and yi means y of 0, right? So y of 0.5 is y of 0. What is y of 0? Y of 0 is given to you as initial value is 0. 0 plus 0.5 f of 0, y0 is 0. Y of 0.5 equals to 0.5 into f. Now, what is f? Just remember this one. F is your the dy by dt function, right? So f of 0 comma 0 is how much? So here your f is only a function of y. It can be a function of t also. So that's why we are writing it f of ti. Right here, it is not xi, it is rather ti. So we'll be writing it ti comma yi, right? So that is the thing. So 0.5 f of 0 comma 0. That means ti is 0, yi is 0. So if you substitute it here, you will get 0.5 into 2.5. So y of 0.5 is 1.25. So is the application of this formula clear to you?
Yeah. Understood.
Understood, right? So next step, can you tell me how means what is the thing we'll do? It will be y of 1, right? So it will be y of 0.5 plus h into f of this is 1 second. This is 0.5 y of 0.5. So this step will be finding out y of 1, right? Y of 0.5 from the previous step we will get this 1.25 0.5 f of 0.5 comma 1.25. So y of 1 is 1.25 plus. So what is f of 0.5 comma 1.25? In place of y we'll be replacing 1.25, right? 2.5 minus 0.1 into 1.25. 2.34375. 2. This is 1.171875. So y of 1 will be equal to 2.422. This is the third step. Now if we go to, this is the second step, sorry. Now if you go to third step, y of 1.5. What will be y of 1.5? It will be y of 1, h f of 1, comma y of 1, right? So y of 1.5 is, y of 1 is 2.422, 0.5 f of 1 comma 2.422. 1.5, 2.422 plus 2.5 minus 0.1 into 0.5. 6.9567. So it is 2.422 plus 0.9567. 3.378. 3.379 rather. So here y of 1.5 we are getting as 3.379. Now we'll go to the last step, right? So till 1.5 we have got. Now the last step we'll be finding out y of 2. Y of 2 will be y of 1.5 plus f of 1.5 y of 1.5. So it is 3.379 of 1.5 3.379. So y of 2 will be equal to so this is 4.05. So y of 2 using Euler's technique and h equal to 0.5 we are getting as 4.058 and true value was given to us as 3.808. So you can see we can find out the error. percentage error, right? So it is mod of 3.808 4.058 divided by true value into 100%. So this, if you calculate, 6.57%. So you can see the error is 6.57%. So it is not very less. So since we have this Euler's technique inbuilt, it has the error quantity is more. But since we have used a lower value of h comparatively, we have got a lesser error. So now we will see here, if we take h equal to 1, what will happen? First we'll take with h equal to 2, then we'll see with h equal to 1. So h equal to 1, right? So we have to go from 0 to 2, and this is the first value. So this will be in one step only, right? So 0 plus h is the next step. So y of 2 is equal to y of 0 h into f of, so y of 2 is y of 0 plus h into f of 0 comma y of 0. So y of 2 will be y of 0 is 0, h is 0.5, f of 0 comma 0. Y of 2 is how much? Oh, sorry, h is not 0.5 here, h is 2. So 2 into f of 0 is, what is the equation? 2.5. So y of 2 we are getting as 5.0, and your true value is 3.808. So you can see here the error is more. 0.808 0 by 3.8. Here the error is 31.3%. So you can see here, just we have increased the error, the step size from 0.5 to 2. That is 4 times we have increased, whereas our error has increased by almost 25%, right? So here, if you program, if you program it, and if you see for different values of h, what is the value of error? So we can do that easily in our MATLAB programming. So we can see here our error is proportional to the square of h in Euler's method. I'll just come back 2 minutes, Nasim.
Yeah, yeah, sure.
Sorry for the delay. You are here, right, Nasim?
Yeah, I'm present.
So as I was telling, this error is proportional to the square of the step size, right? So as you decrease h, your error will get reduced, and we showed that by one example. So now another example we'll see your RK2 method or Hume's method. RK2 method or Hume's method. So we will see here. So we'll take the same differential equation. So we'll take the same differential equation and we'll see how to find using our Hume's method or the second order RK method. So y of 0 is given as 0. So we have to find out y of 2, right? So first we'll do using step size h equal to 1. That is our problem will be solved in 2 steps, from 0 to 1, then 1 to 2. Okay. So here, two variables we will be introducing here for our easiness, K1 and K2. Okay. So what is K1? K1 is f of xi, comma yi. So I is presently 0, right? So it is x of 0, y of 0. This is K1. That is f of 0, comma 0. So it is basically 2.5. K2 is f of 1, comma your this rather this is not 1. 1 second. Just a second. Yeah. So this is xi plus h, comma yi plus h times k1. This is k2. So what is xi here? Xi is x0, that is 0. 0 plus h. H is 1. So it is 1. Yi, that is y of 0, right? Y of 0 is 0. 0 plus h is 1 and k1 is 2.5. 0 plus yi is 0, h is 1 into 2.5. So f of 1 comma 2.5. So f of 1 comma 2.5 means f of 2.5, and that is how much? F of 2.5 is 2.5.1. So it is 1.875. Clear? Is it clear? The equations what I am writing. So the derivations of this RK2, RK4 method, those are very complicated. So we cannot do that in this. It is beyond the scope of this particular class. You can refer to any book, any differential equation, numerical differential equation book. You can easily get it there. So just you have to learn here how to apply this formula to your equation, to your problem.
Can you repeat that K2 variable? Just
Yeah. So K1 is basically f of xi yi and K2
yeah.
is f of xi plus h yi plus hk1. So xi plus h is xi is x0, right? X0 is 0. So 0 plus h 1 and yi is y of 0. That is 0 again. So 0 plus h is 1 and k1 is 2.5 from the last step. So f of 1 comma 2.5 and f is this slope function. So t is not important, x is not important here rather. So it is 2.5, f of 2.5. So that gives me 1.875. Clear?
Okay, so here we are substituting one variable in another, like
Yeah, yeah.
K1 in K2.
Yes.
Okay.
So now my y of I plus 1 is yi plus half into k1 plus h by 2 into k1 plus k2. That is k1 and k2 are the two slopes, one at xi yi and the other at xi plus h and yi plus hk1. So these are the two intermediate points we were talking about. So here we are finding out the slope. So now this is y of 1 equal to y of 0. H is 1 by 2, 2.5, 1.87. So if you just substitute this, y of 0 is 0. So it is 2.5 plus 1.875 divided by 2. So it is 2.1875. So now this is for h equal to 1. That is y of 1 we have found out. So this is step 1. That is I equal to 0. 0th step. Now we'll go to second one, I equal to 1. So again we have to repeat the same thing. So what is k1 now? F of x1 y1. What is x1? X1 is 1, right? F of 1 comma y of 1. Y of 1 we have found out here, right? 1 comma 2.1875. So what is f of this one? 2.5. So it is 2.021. K2 is f of, just be careful with this one, x1 plus h, y1 plus h times k1. So x1 is how much? 1. 1 plus h is 2 because h is also 1. Y1, that is y of 1, that is 2.1875 plus h is 1, k1, 2.0. So this is basically f of 2 comma 2.1875, 2.021. That is 4.2085. So it is f of 2 comma 4.2085. So it is 0.1 into 4.2085. This is 0.7289. K1 and K2 we have got. Now we will substitute this. Yi plus 1, yi, h by 2, k1 plus k2. So this is y of 2 of 1, 1 by 2, k1 is how much? 2.021 and 0.7289, 2.0. So it is basically y of 1 was how much? 2.1875. 2.1875 plus 2.021 plus 0.7289 divided by 1.37495. 2.1875, 1.37495. So it is 3.56. So this is the value of y of 2 which we are getting by our RK2 method. So error, if we want to find out, error is how much? True value is 3.808. See, the error is very less here. Even if we are using a large step size only, we are not using a small step size. So we are using one, that is 2 steps we are doing. It is 3.808, 3.562 upon 3.808. So error is 6.46. See, here error is in RK2 method using h equal to 1, your error is 6%, 6.4. Whereas in Euler's method we saw with h equal to 0.5, that is half of the present step size, we were getting almost the same error, 6.5%. So you can understand here that this RK2 method is a better approximation. Had we taken h equal to 0.5 in this RK2 method, we would have got a much lower amount of error, because with h equal to 1 itself we are getting 6. So with h equal to 0.5, we would have got much lesser error, right? So is this clear to you?
Yeah. I wanted to ask that it is called RK2 because we are using just two variables.
Not two variables, as I explained just a second. So If you see this graphical approach here, so what we were doing is between Tn and Tn plus 1, we were making a subinterval, right? So since there are two subintervals here, that is, we are finding the slope at this point, that is yn plus 1, which is k1 here, and also at this point, that is the intermediate point. That's why this value gives me k1. If you look into the derivation, so some part I'll describe about k1 and k2, how you are getting it. So we'll see there. So since there are 2 points at which we are dividing, which we are finding the slope, it is known as RK2 method. If you see RK4 method, we'll be dividing this the gap between this Tn and Tn plus 1 into 4 subintervals. And then we'll be having K1, K2, K3 and K4 there. So there we will see how we are, why it is RK2 and RK4. Is it clear?
Okay, yeah, clear.
Clear, right? Okay. Now we will see RK4 method. Okay. Okay. Before this, so since you asked me about this, why it is RK2, so I'll explain that. I'll try to explain it graphically. Okay. Just listen here. So this is my function. Here we have En. Suppose here we have Tn plus 1. This is my Yn. This is my Yn plus 1. Okay. So now in RK2 method, what I told, we will be dividing into two subintervals, right? So first we'll draw the tangent, that is the slope of the curve at here. This is my point, right? This is the point. Suppose this is the point, right? So now this is H. So we'll be dividing this into two intervals. It is not the midpoint. Just remember this. It necessarily does not have to be the midpoint. So now suppose we are taking that we have divided in the ratio of P is to Q. Okay, so this length is P times H because the total length is H. This part is PH. This part is QH. Okay. So this is PH, this is QH. And 1 second. This YN line we will draw here, we'll need it. Okay, so this is the YN line, right? So now this is my YN, correct? So this is my YN, and this is YN plus 1 I've already marked. So now this is my QH, right? And this point is my second point where I am trying to evaluate the slope, correct? So this coordinate and this, if I draw here, just it is difficult, I'll just zoom in. So this length I am telling it is QH into K1. Some K1 I'm taking. There is a particular value. There is a random value I am taking. K1. Okay. Okay. K1 is not a random value. K1 is the slope of the function at this point. So if K1 is the slope of the function at this point, by geometry, we can find out that this distance is QH times K1. Okay. So if this is QH K1, this is my HK1. And so this line YN plus HK1. So this point is the point at this green point where we have marked the arrow. This is the point where we are trying to find the slope. So if you can see what is the x coordinate of this arrow marked point, it is Tn plus Ph, and the y coordinate is Yn plus QHK1. So this is the point at which we are trying to find the slope. Just I'll upload these notes. Now it might be difficult for you to understand. You can go back and you can have a look at it again. Okay. So what was my this equation according to this Euler's thing? It is Yn plus 1 plus h into y dash. So this is y dash bar I am writing because it is the average of the weighted average, right? So this is unknown to me. So now this y dash, since it is a function of Tn, Yn, and also the step size. So we have to find this y dash, right? So it is weighted average of slopes at, in RK2, it is at 2 points, Yn and Yn plus this new point. Here we are trying to find the slope. So now, so we are first we are defining one variable which is K1, which is the slope of the function at the normal thing, Tn, Yn. That is what is whatever is given to you. Next is slope the intermediate point. It is Tn plus Ph, Yn plus QH, K1. So this is given by K2, which is f of Tn plus Ph, Yn plus QH, K1. Is it clear? Or am I going too fast?
No, clear, understood.
Okay. So this is my intermediate point, slope at the intermediate point. So now, in order to find this intermediate point, the slope at the intermediate point, first we need to know what is that point. So what is the coordinate of the point? It is Tn plus Ph and Yn plus QH K1, right? So for that, we need to find out P and Q. K1 is known to us, T and Yn, H, everything is known to us. So we need to determine P and Q, right? So we will see here how we can find out. I'll not go into the detailed derivation of how to find out P and Q. We'll just see, I'll just tell you. So based on the derivations, based on derivations, we can find out. So just remember here, apart from P and Q, there was two more variables, which is A and B. So here, this actually here, this we can, this Yn plus 1, we can write like this. Yn plus 1 will be Yn plus H into AK1 plus BK. Right, this y dash bar, which is unknown to us, that is the slope at the intermediate, the slope at the weighted average, the weighted averaged slopes at the T and Yn and the new intermediate point. So that we can write in terms of K1 and K2 with some coefficients. So y bar dash will be AK1 plus BK2. So in order to find out K2, we need P and Q. And in order to find out Yn plus 1, the entire this basis of the RK2 method, we need A and B also, right? So based on the derivations, A and B have been found to be equal to half, and P and Q have been found to be equal to 1. So basically, if P and Q is 1, that intermediate point is the midpoint of the two parts of the two of Tn and Tn plus 1. So if we substitute this, what was my Yn plus H into AK1 plus PK2, right? So Yn plus 1 was equal to Yn. H, A and B are half, so it is H by 2 K1 plus K2, where this is the iterative equation where K1 equal to slope at Tn Yn and K2 equal to slope at the intermediate point. Tn plus PH, P is 1, so Tn plus H, and QH K1, so Yn plus HK. So this is the derivation, or little bit understanding you can say. The entire derivation I'm not doing here. So this is the point. So this is from where the formula came actually for RK2 method. Clear?
Okay. Yeah, clear.
So this geometrical approach is a little bit difficult to understand. You can just go back and you can see the recording once again. If it is not clear, you can come back to me in the next class. Okay.
Okay.
So now you can see that RK2 method, the geometrical approach is very complex. So in RK4 method, we'll have 4 subintervals. So it is very difficult to understand. So we'll not go into the this geometrical approach of RK4 method. We'll just look into the equations. So in like in RK2, we had K1 and K2 only, right? So in RK4, we'll have 4 variables, K1, 4 slopes, K3 and K4. So K1 is always the slope at Tn, Yn. This K2 is Tn plus H by 2 and Yn plus H by 2 K1. K3 is slope at Tn plus H by 2, Yn plus H by 2 K2. K4 is x coordinate is same for all, Yn plus HK3. So the iterative formula here is Yn plus 1 equal to Yn H into K1 by 6 plus K2 by 3 plus K3 by 3 plus K4 by 6. So this is my iterative formula for. This is the formula for RK4 method. So this is for one step. So if there are multiple steps, all these 4 variables will again change. Next step, again we have to evaluate K1, K2, K3, K4, then we'll get Yn plus 1. So I'll do one problem so that it will be clear to you. So I'll take the same equation. What was the equation? Dy by dt 2.5 y of 0 was 0. So I'm taking h equal to 2 directly. So we'll be having only one step, right? So we'll see here in one step only how much error we are able to reduce in RK4. RK4 is the most superior method. So what is K1? K1 is Ti, Yi, right? So it is f of 0, y of 0. So it is f of 0, comma 0 is 2.5. What is K2? So you can see the formula here. Tn plus h by 2. So 0 plus h by 2. H is 2. So it is 1. And y of n, which is y of 0, plus h k1, right? H by 2 k1. So it is k1. F of 1, comma y of 0 is 0. K1 is 2.5. So it will come out to be 1.87. What is K3? K3 is again x is same. This is Yn. Yn is y of 0 plus h by 2 K2. So h is 2, 2 by 2, 1, K2. K2 is 1.87. So it is basically f of 1 comma 1.875. So it is 2.1484. A4 is f of 1 comma y of 0 plus, it is not h by 2 here, it is h. So h is 2.148. So if you substitute this, this will come to be 0.6536. So K1, K2, K3, K4, all you have got. So now you can just substitute here y of 2 equal to y of 0 plus h by 6 into K1. Sorry, what was the equation? H by h into K1 by 6, K2, or we can just take 6 outside. It will be K1 plus 2K2 plus 2K3 plus K4. So if you substitute this, y of 0 is 0, h is 2, 2 by 6, K1, K2, K3, K4. 2.5 also. 5 plus 2 into 1.875 is 3.75. Next is 2.1484. 2 into is A4 is 0.6536. If you substitute this, you are getting 3.7333. This is y of 2. So what was my true value? True value was 3.808. So you can understand error is very less here. This is basically 3.733 minus 3.808. So error is only 1.96. Just by using h equal to 2 in one step only, we got the error to be so less, 1.96%. So we can write here RK4 method is the most accurate. Is the most accurate method. So you can understand if we use h equal to 0.5, so error will be very, very negligible, right? Okay. So this is all about today. Any questions, any clarifications you want from the assignments, anything? Time is there, you can ask me.
In solving any numerical, like whenever you are using numerical methods, so up to how much error it is accepted?
That depends actually. It will be if it is asked in a question in the exam. If it is asked, the tolerance level will be generally given to you. So anything below 0.1% is acceptable.
Okay, 0.1%.
Yeah. So your accuracy has to be, means suppose any engineering problem or any real life practical problem you are solving using numerical technique. So there your error should be less than or equal to 0.1%. So that is the general conception which is taken.
Okay. And in RK4 method, it is just for one step. If we are
No, it
doing
is not for one
means
step.
two
So
step,
here
not
the why
one
is it
step
one
size.
step? Because we took h equal to 2 here.
Yeah, yeah.
So if you'd have taken lower value of h, say h equal to 1, then we would have to do 2 steps because 0 to 1, 1 to 2.
Okay, okay. So we will have
Depending on the
means
value of
more
h, your
number of
number of steps will be decided. Yes?
means there will be more variables and more calculation in that. So
Yeah,
that
more
will be more
calculations will
efficient.
be there. Yes, yes. Computationally, if you see,
Okay, okay.
RK4 is a bit expensive, but again, you have your computer programs, right? It can do in fraction of seconds. So what I will do is,
But
2 more classes are remaining, right? So next Saturday
yeah,
I'll
yeah.
take, but next to next Saturday I'll not be taking. I'll be compensating it in the that week Monday I will take most probably. That I'll inform you. And one extra class I will
Okay,
take, which is the on 19th of this October. There I'll be all these techniques I'll be discussing how we can solve in MATLAB. So based on that MATLAB
yes,
programming, little bit I'll 1 hour session I'll take. So that will do. Is it fine for you?
yeah, sure.
Okay. So next class will be on same time, but next to next class I'll try to reschedule that. Okay.
Okay, sure.
Okay. Fine. Okay then. Today I'll close the class. Next week we'll meet again. Bye.
Okay.